the chain rule. So this is like you have two functions of x and you want to differentiate, you have their product and you want to differentiate them. So what you're going to do, that this is going to be the derivative of x with respect to x, which is going to be 1 multiplied by y plus x times, what do you call, dy by dx actually, okay, plus dy square by dx. So this is like a function of x composed with the square actually function actually, or x square, okay. So you're going to apply that. So this is like this situation, f of x raised to x square. And you know that how to differentiate is that you differentiate this square function, evaluate it at f of x and multiply with f of x. So in other words, you can do this is really what you call 2y multiplied by dy by dx and everything equal to 0. Okay. So in other words, why this expression is equal to this, I want you to keep the reasoning in your head actually. Okay. So you should know the reasons as well, that why this y square becomes 2y and why this dy by dx is coming with it actually. So there is it's really a consequence of chain rule. Okay, so what is your objective? So you had such an implicit function, your objective is to find dy by dx. And for finding dy by dx, you need to just simply isolate this dy by dx actually. So what you need to do, you need to send everything on other side except dy by dx actually. So it's going to be dy by dx. So this will go on other side, so it's going to be negative y, negative 2x and minus 2x. And you can treat this as x plus 2y, okay, so by distributive law, and just throw this x plus 2y on other side, so it will be moved from here and you're going to have this x plus 2y in the denominator here actually. Is it making sense? Okay. So I hope it is making sense to you. So this was the recipe that we did for what do you call for the implicit differentiation. So we did many problems. I'm not going to get into more into it. Okay, and okay. So this was the basic thing that we did. Where we ended our discussion, the very last discussion was really on what do you call the inverse trigonometric functions actually. Trigonometric functions. So this was the last point where we ended actually that thing. And how did we, so for example, do it? So imagine I have a function, say, which is called sine x, okay. Then I know that this sinusoidal function, okay, this sinusoidal function, that it starts from 0. So if this is 0, this is pi by 2, this is pi, and this is, say, for example, 3 pi by 2, and this is, say, 2 pi, okay. Then this function starts from 0, goes to its highest value 1 at pi by 2, get back to 0 again, okay, and goes to its least value, which is negative 1 at pi by 2. So this is really positive 1 and this is really what you call negative 1, and then goes back to 0, okay, at 2 pi. And then it just keeps on, what do you call, oscillating actually. Okay, it just keeps on oscillating. So if you have a function sine x, then we know that the domain of the sine x is the entire real line actually. Okay, so there is no point where the value of the function doesn't exist. So this just goes on forever. Okay, so on the both sides, here and here. And the range, the outputs of the function always, it just oscillates between these two values, negative 1 and 1. So this is what really is the question. And if I ask from you, what is the evidence that sine x is a function, then you must have learned, and we discussed this in our class as well, what you call the vertical line test actually. So if you have given, for example, a scrabbled piece in two-dimensional plane actually, something is scrabbled, then how you can know that whether this given picture is a function or not. So you just need to check that do for every input you have a unique output. The answer is yes actually. If you for example take a point and draw a vertical line, this vertical line is going to hit at a unique point on this curve actually. So if you have something like this, then this is not a function. Why? Because if you draw a vertical line at a point actually it just hits the curve at 2 points actually. In other words, it violates the definition of being function, that for one input you are getting the two outputs actually. Okay, so that's a function. So this is my x-axis and this is my y-axis. Now, how can I find the inverse of such a function actually? Okay. So for example, this guy is not a function. So what would be the inverse of it? So there are various ways to find the inverses of the function, but we discussed and we spent a lot of time on discussing one way to evaluate the inverse of the function was really to say that, okay, take this graph and just rotate it 90 degree. Okay? Just rotate it 90 degree. In other words, if I treat this as my y-axis and this as my x-axis, would that be a function? Now you're going to say that, so in other words, instead of looking, so the graph is same, okay, but you are looking at from the different perspectives. So whatever was the range become domain, okay, and whatever was domain, so it is really the codomain actually. So the question is this scrabbled piece in this new xy space a function? The answer is okay. Let's try to have a vertical line test actually. In other words, try to draw a line on the set of inputs and see that whether that line, vertical line, which is horizontal in this case. I mean, what you can do, you can just rotate it actually. Okay, so you can draw this, for example, picture on a page, okay, and just rotate it and ask the same question that you were asking before. Is this given picture is a function or not? The answer is that this would not be a function, because for every unique input you are getting, two outputs. So no matter where you go, this is not really a function. Okay? There is only one way that it would be a function, that if, for example, you get rid of really this part, the rest of the part. Okay? So in other words, you take away the controversial points. Now, so if you treat this part of the graph, okay, with the domain say -1 to 1, okay, then this is really a function, because for every unique point you have an output, okay, a unique output. So that's really a function. For every input you have a unique output actually. Are you getting the point? Okay. You can redraw the same picture and try to redraw it, and we did a lot of this practice in our normal class actually. Okay, so you have to be very careful while redrawing it. So so try to redraw this picture instead of say x-axis being here and y-axis being here. Try to redraw it, for example, where x-axis being here and y-axis being here actually. Then how does it going to look like? This is going to look like that on the interval say -1 to 1, so the -1 is here and 1 is here. Okay, this function would, you know, somehow look like, you know, something like this actually. Okay, something like this. So this is really the inverse of the function actually. Okay, the inverse of the function. Okay, let me talk a little bit more about it. So the inverse of the sine function, let me give it the name sine inverse. When evaluated at x, has a domain. What is the domain of it? So the domain of it is really between -1 and 1. So it exists here, which is really here. Okay, between say -1 to 1. Okay, and the range of this function is really what? So the range of this function is, okay, so you can treat the range of this function as what? Okay, so this is between
either pi by 2 to 3 pi by 2 or
pi by 2 to 3 pi by 2. Okay, so
or minus pi by 2 to plus pi by 2.
So it depends on where you want to look at it. Okay, so say in its current form it is something between
Pi by 2 and 3 pi by 2.
Pi by 2 to 3 pi by 2 actually. Okay, but you can also, by twerking this, you can also get this range on between say minus pi by 2 to plus pi by 2 actually. So in other words, it just exists on an interval of length pi, so which starts from say pi by 2 and ends at 3 pi by 2. So it just exists on any interval of what you call pi actually. So what do you mean by that? Since, okay, so here's the thing, and I must clarify this point. Since this function is always kind of oscillating, okay, something like that, then is it necessary that I should only take this part and become a function? So in other words, I draw the rest of the part, okay, no. So I can draw all this part and get a function. But I can do another thing actually. I can only take this part actually and draw the rest of the thing. So this would be still a function. Are you getting the point? This would be still a function. But that would be a function, you know, whose outputs are between minus pi by 2 to pi by 2. So you have to just take any interval of length pi, okay, and you're going to have a function actually. So therefore, you're going to say that the range of this function is really between pi by 2 to 3 pi by 2. I know it's a bit confusing, but if you're going to think carefully about it, you're going to repeatedly listen this argument, I hope you're going to get this actually. Okay. So similarly, you can do this about the same about the cos, you can do the same about the tangent and cosines and sines and so on and so forth actually. Okay. So why we are interested in inverse trigonometric functions at this point? Because what I would like to do, I would like to find the derivative of the inverse trigonometric function. So this is what that I would like to do. To give you a more of the glimpse of the inverse trigonometric function, we can think of, for example, if I am saying that, okay, what is the sine inverse of 0? So when you are, for example, computing the sine inverse of 0, you are asking a question, okay, so in other words, it's going to be something, let's call this y. But what is this y? This y is going to be an angle. Okay, is going to be an angle. So what is the angle that gives you 0? Okay, so sine inverse of 0 is y. Then you are basically asking that what is the y? In other words, what angle of the sine would give you 0 as an output actually? So you're going to say that, okay, say y equal to 0, is going to give me, so y must be 0. In other words, that sine inverse of 0 is really what you call 0. You can ask a question, what is the sine inverse of say -1? By the way, sine inverse of 0 can be 0, but it also can be a pi. Okay, it depends on that what range you are taking actually. Okay, so say for example, so what would be sine inverse of 1? So in other words, what angle of the sine would give you, -1? In other words, what input should I put inside the sine function so that I can get a -1, what you call output actually. Now, I mean, if you see if this, function goes on forever, then you have a different choice. For example, you are getting -1 at say 3 pi by 2, but you are also getting -1 at, for example, negative pi by 2 actually. Okay, so if this is pi by 2, then this is 0, then this is really negative pi by 2 as well. Okay, so you have multiple answers for it actually. Okay, so you always have to look that, okay, what part of graph you are considering actually. So imagine if you are only considering this part of the graph, then there is only one choice actually, where the sine inverse of -1 or the sine function will give you -1, that is, for example, 3 pi by 2. But if you are considering the entire sine curve, you can draw it on, for example, your Desmos, and you can have a look. Then you have different choices. That sine function is -1 at negative pi by 2, it's also -1 at 3 pi by 2, and so on and so forth. So you have different choices. So I can say the sine inverse of -1 is really, say, for example, 3 pi by 2, it could be, negative pi by 2, negative 3 pi by 2, so on and so forth. So there can be, many, angles actually. So when you are computing, say, sine inverse of some x, what actually you are saying that, okay, what angle when I substitute into the sine would give me x actually. So if you give that angle a name y, what actually you are saying, so sine inverse of x is going to be y, if and only if y is that angle. If you substitute that y into the sine function, it's going to spit out x actually. Okay? You're going to spit out, what do you call, x. Now, you can ask all kind of interesting questions about sine x. Say, what would be the sine inverse evaluated at sine x actually? Okay. Here's an interesting question. What angle of sine would give you the value sine x? Okay. What angle of y would give you, for example, sine x? Then naturally you're going to say x is that angle actually. Because think about it. Because if in sine you substitute x, you're going to get sine x actually. So therefore, the sine inverse of sine x is really x. Okay? And you can also think from a similar perspective that, okay, if you have a sine inverse of x, sine of evaluated at sine inverse of x, then this would be x as well. Because sine inverse of x is what? What angle would give you x? So let's call that angle y. Okay? Let's call that angle, for example, y. And since the sine inverse of x, say, is y, that means that sine y is really, what do you call, x actually. So how are you going to interpret it? And what would, okay, so if the sine inverse of, if you give this guy a name y, so like sine inverse of x is y, and then this expression will become what? Sine y. Okay? But sine y is really x actually. Think about it. So this will become x. okay, by really the definition. So the sine of sine inverse of x is really giving you x actually, okay. So this really shows that this inverse sine function and sine and inverse function are the inverses of each other actually. So they are inverses of each other, okay. And anyway, so we had this discussion in detail in our last discussion. So far I have spent a lot of time on recalling the previous stuff. So what is our major question that we will like to deal actually? So the major question that we will like to deal is really that imagine if we have been given a function y equal to sine inverse of x, okay, then how to compute the derivative of such kind of function. Okay. The key trick here to find this expression sine x dy by dx is to treat this function as an implicit function actually. How? So think about it, we just showed that if the sine inverse of x is y, what actually you are saying that what angle when substituted in sine would give you x, and that angle is y. So in other words, sine y is x. So if the y is sine inverse of x, that means that sine y is really x. Okay? So I don't know how to differentiate sine inverse of x, but I really know that how to differentiate sine y actually and x. And what you can do is that differentiate both sides with respect to x. So sine y and dx by dx actually. Where y is what? Y is a function of x. So this is really a situation like sine f of x. So how to differentiate this? So we know that we need to apply chain rule. So cos and substitute say y into it, and this is going to be dy by dx. So cos y and the derivative of the underlying function. Okay, so for example, if you have sine f of x, you're going to say you have a cosine f of x multiplied by the derivative of f of x actually. So you are doing the same, equal to what you call 1. So what you need to do now I can separate this dy by dx. So what would be this? So it's going to be dy by dx is going to be 1 over cosine of y. Okay. Now one of the things that you can say is that I want dy by dx as a function of x, because y is a function of x, then I also want dy by dx as a function of x, while this is at the moment it is a function of y. So how can I turn this function in the terms of what do you call x? We all know the elementary identity. I mean, if you remember, so we know that if I have a sine square of something plus cosine square of something, that is always going to be 1. So that is always going to be 1. So sine square y plus cos square y is going to be 1. So from this I can deduce that cosine square y is going to be square root of 1 minus sine square y. Okay. So from this I can deduce, so if sine square y plus cosine square is 1, then cosine square y is 1 minus sine square y, and the cosine y is going to be the square root of 1 minus sine square y. So I can replace this guy by a square root of 1 minus sine square y. Okay, so I just used my trigonometric identity. Now, do I know something interesting about sine y? The answer is yes, that sine y is always x. So hence, I can say that this is going to be square root of 1 minus x square. So square root of 1 over 1 minus x square. So in other words, what is the derivative of sine inverse of x is going to be 1 over square root of 1 minus x square actually. So trick is what? The trick is pretty easy. So I wanted to differentiate sine inverse x, so I gave it a name y. So if y is sine inverse x, then this means that the y is the angle when it's substituted in sine would give you x. In other words, sine y is x. And then I did the implicit differentiation, derivate both sides. So it's going to be cosine y dy by dx, and this is going to be 1. So the dy by dx is going to be 1 over cosine y. The key trick is really to convert now this cosine y or your given function in the terms of the x actually. So since I know that sine y is x, so can I express cosine in the terms of the sine so that I can express it in the terms of the x? So I know that cosine square plus sine square is 1. So the cosine y is going to be square root of 1 minus sine square y. So it's going to be 1 minus x square. So this would be really the derivative d by dx as sine inverse x is really 1 over square root of 1 minus x square. Okay, so that was it about the inverse trigonometric function y. We can talk about the other inverse trigonometric functions as well. For example, what would be the cosine inverse of x. Okay, cosine inverse of x. So the cosine inverse of x, we know that for the cosine inverse of x, it starts from 0, it starts from 1, goes to 0 at pi by 2, goes to negative 1 at pi, goes to 0 at 3 pi by 2, and goes to 1 back again at pi. So this goes like that actually. Okay, something like that. So I think we can make a smooth curve actually. So you can say that it goes to 0 and goes back to 1 at this point. So it's going to be something like that. And it obviously goes on forever actually. So on both sides, we can have this all the time actually. It goes on in all directions. Okay? But it is 0, at 1 at 0, and at pi by 2 it is 0, at 3 pi by, pi it is negative 1, at 3 pi by 2 it's again 0, and at 2 pi it is again 1 actually. So that's how it goes. Now I want to turn this into a function. So what can I do? So here's the same recipe is this. Either consider this piece, that would be a function, or consider this piece, that would be a function, or consider this piece, that would be a function. You're getting the point? So you can play precisely the same game that you played with what do you call cosine of x actually, sine of x. Okay, and something. So if I have the cosine inverse of x, then what is the domain of it? Domain of it again, no matter what piece you take, is always going to be between 1 and negative 1. Okay, 1 and negative 1 to 1. Okay, and the range of it is going to be between what? It depends on what part you are taking. So it could be between 0 to pi. Okay, it could be between pi to 2 pi. It could be between say 0 to negative pi to 0, and so on and so forth actually. Okay, so the domain of this could be what we call 0 to pi actually. Okay, I think we must exclude this pi from here, otherwise 2 points are going to have the same output actually. So should exclude the pi from it. So this could be the range of it. And here's an exercise for you to do. that show that if you compute the derivative of the cosine inverse of x, okay, so it is going to be negative 1 over square root of 1 minus x square actually. Okay, so it's going to be negative 1 over 1 minus x square. So this is what that you have to show. You can use the precisely same argument that we used previously about